Hello. In today's lecture, I will be focusing on the following topics. Firstly, I will be having a discussion on the noise suppression effects of frequency modulation. Then I will be focusing on the noise and phase shift terminologies. And thirdly, the focus will be on the Preemphasis and Deemphasis circuit, which will be followed by the topics on the frequency modulations comparison with amplitude modulation, and later in the last I will be doing a discussion on the applications of frequency modulation along with amplitude modulation. So let's start from the first topic, which is the noise suppression effects of frequency modulation. Noise is basically a kind of signal which is generated by lightning, motors, automobile and ignition engines, and it can be introduced also due to multiple power line switching as well, and there are different devices which are producing the noise at their own capacity, and there is a noise also present in the wireless communication. In the space there is some noise signal, and the purpose of that signal is to attenuate and distort the information signal which is communicating from the transmitter to the receiver wirelessly. Noise is a kind of, if we can see it diagrammatically, then it is a kind of a narrow signal which is for a very short duration of voltage, and it is having a very high amplitude, or there are multiple frequencies and multiple amplitudes along with multiple phase signals. A noise is basically a kind of random signal, so mostly it is a kind of short duration high altitude wave which happens for a short duration of time. So these small durations of voltage spikes or amplitudes of the noise, when add up in the signal, it can attenuate it, it can distort it, and it can change its shape, and so the noise uh, can change the information by superimposing on it, and sometimes if the noise is too much higher, then it can completely attenuate the information signal, and the signal is useless for communication, and it is an unintelligible signal which cannot be recovered on the receiver side. Similarly, if we can see an FM signal, which is a frequency modulation signal, it has a constant amplitude, and the information is basically focused on the frequency of the modulated signal, and it is not focused on the phase of the modulated signal and the amplitude of the modulated signal. As in amplitude modulated signal, the information is focused on the amplitude of the modulator, so FM signal is somewhat immune in this case from the noise, and there is a fact that the noise affects the high frequency components of the frequency modulated wave, and for that purpose on the receiver side, when the FM modulated signal is transmitted from the transmitter and it is going from the wireless channel to the receiver, at the receiver side we have a limiter circuit which does what? It restricts the high altitude component of the received signal. We can see that thing diagrammatically over here. If you can see at the figure, you will see that if this is a kind of wave which is the FM modulated wave received on the receiver side, then you can see over here the noise spikes, which is the high altitude amplitudes, and these are due to the introduction of noise when this signal was passing from the transmitter to the receiver, and at the receiver side there is a limiter circuit which does what? It only allows the signal which is between this limitation to pass through it, and then clips the above or high frequency altitude components. So any amplitude variation which is occurring in the FM modulated signal are being clipped by the limiter circuit. In this way the noise is reduced in the frequency modulated signal, and the clipping has been done, and this clipping has no effect over the information content of the FM signal, because the information is solely based on the frequency variations of the carrier signal. So this is a diagrammatic representation of the same figure which was discussed earlier, where the limiter circuit clips the high altitude components which are due to noise happened in the FM modulated signal. So now we will be discussing the second topic, which is the noise and the phase shift terminologies, and for that we can see the book over here, and for that you have to understand this figure. If we have a carrier signal which is represented by S and the noise which is represented by N, then the overall signal which will be a composite signal under these two signals will be C, and phi is the angle between C and the S, which is the carrier, and this angle will be maximum when the noise will be at right angle to the carrier S, and this can be calculated by phi is equal to sine inverse N by C. So why we are discussing this? Because uh, the noise can generate a phase shift in the carrier signal, and this phase shift can be calculated by this formula, and this phase shift can be uh, used to calculate the frequency variation, because when this phase shift which is introduced by the noise is multiplied by the modulating signal frequency, we can see that there will be a new value which will arrive over here, which is the frequency deviation produced by the noise. As we know that in frequency modulated wave, the information is solely based on the frequency deviation of the carrier. So when the frequency deviation which is introduced by the phase shift of the noise, when this is added into the FM modulated wave, then it will generally cause a frequency deviation. So when this frequency deviation occurs, if we can see uh, uh, if we can do an exercise over here and we see what this response can do, what a noise can do with an FM signal, we can assume a signal to noise ratio of 3:1 and the modulating signal frequency equal to 800 Hertz. Then we can see by this formula, if the noise is 1:3 with the signal, then we have a phase shift which is 19.47 degree is introduced by the noise, and when this phase shift in degrees is converted into radians by dividing it with 57.3, we have 0.34 radians, and when we have this phi which is the phase shift in radians multiplied by the modulating signal frequency by using this expression, then we can get the frequency deviation introduced by the noise. So due to this noise we get the frequency deviation of 271.8 Hertz, and if we assume that the maximum allowed frequency deviation in the FM modulated signal is 5 kilohertz, then we can see the percentage of this 271 from that deviation, which is 5 kilohertz. Then we can see over here that it is somewhat a bit close or higher than 5%, and if we see that it is, we see that closely, then we can observe that this is the noise frequency variation and this is the signal frequency variation. The signal frequency variation is 5 kilohertz and the noise frequency variation is 0.2 kilohertz, and we can say it that this is N by S, and if we want to calculate the S by n from it, then we can get it from this expression, which is 18.4. So what we have seen over here, that for FM scenario, when we have a signal to noise ratio of 3:1, then it can be translated and transformed into a signal to noise ratio of 18:4 to 1, and that is the case why the FM signal is immune to noise over here. Here we can see that the signal has been, the ratio has of the signal has been increased from 3 to 18.4 over here. So one statement I have to put over here, that greater the permitted frequency deviation of a signal in the FM case, the less will be the impact of the noise on the overall signal, and the less the frequency variation, the more will be the impact of the noise on the frequency modulated signal. So we can say it also in a way that higher the number of sidebands, the greater will be the frequency deviation and the less will be the impact of noise on the overall FM modulated signal, and the less the number of sidebands, less will be the frequency deviation and more will be the impact of the noise on the signal. Here there is a numerical which is giving us the signal to noise ratio of 2.8, the modulating frequency of 1.5 kilohertz, and the maximum permitted deviation is 4 kilohertz, and we are able to calculate the frequency deviation of the noise and the improved output signal to noise ratio. By this formula we can just have to put the values and then we can get the phi in radians, and we can use this expression to calculate the frequency deviation produced by the noise, and similarly by this expression we are able to calculate the signal to noise ratio, and it is being done over here. Now our next topic is preemphasis and deemphasis. So in you can see over here that as we know that the noise interferes with the FM signal, and its effect is maximum on the high frequency components of the FM modulated signal, and noise itself is the sharp spikes of energy and contains a lot of harmonics in it. And to overcome the noise on the receiver side, one way is to use a limiter circuit, which we have understood previously in the previous topic, and second way is to introduce the preemphasis circuit on the transmitter side and the deemphasis circuit on the receiver side. So what are the preemphasis and deemphasis circuit doing at the transmitter and the receiver side respectively? We can see a diagram over here. Here on the left hand side we have the preemphasis circuit, which is doing what? That it is the frequency modulator is in the center. When the information signal comes, there is a kind of low pass filter, uh, there is a kind of high pass filter at in the way of the modulating information signal. When we see the preemphasis circuit on the left hand side, then we can see that when the information signal comes, there is a high pass filter in the way of the information signal, whose frequency, cutoff frequency is this, and it does what? That it receives a signal, and when the frequency of the signal is above than a certain level, then it amplifies the high frequency components, while the low frequency components are at some low power level, while the higher frequency components of the modulating information signal are amplified, and then they are being fed to the modulator, which sends the final FM modulated wave into the environment, and in the environment the noise when interacts with the high frequency components, then its effect will be minimal, because the high frequency components, which are representing the high amplitude components of the uh, 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 so when we see the preemphasis circuit on the left hand side, we see that when there is an information signal which comes into the modulator, there is a high pass filter in the way of it, and it does what? That it amplifies the high frequency components of the modulating information signal, and the low frequency components of the modulating signal are kept at low power level, while the higher frequency components are kept at high amplitude level. In this way, when this signal is being fed to the modulator and the final FM modulated wave transmits in the environment, the noise will be having a minimal effect on the high frequency components, and it will be a kind of nice approach over here. Similarly, when the FM modulated signal is received at the demodulator site, then we have a DMC circuit which does what? Is that it attenuates the frequency components which are at high frequency, and the other components are being kept on the same power level. So by this, if we can see that approach of the preemphasis and deemphasis, then we can see this is an amplitude on the y-axis and frequency on the x-axis. Then from a certain frequency in preemphasis, the amplification is being going on, while in deemphasis the attenuation is being going on, and in deemphasis circuit we have a low pass filter over here. So by this effect, by using a limiter circuit on the receiver side and by using preemphasis circuit on the transmitter and deemphasis circuit on the receiver side, we are able to uh, reduce the damage introduced by the noise in the FM scenario. Now I will be focusing on the uh, comparison of the frequency modulation with the amplitude modulation, and we can see the first advantage of the FM modulation is its noise immunity, because the information is solely based on the frequency variation of the FM modulated wave and not on the amplitude variation of the AM modulated wave. So in frequency modulation, the change in amplitude doesn't affect the information signal in FM scenario. So that is a noise immunity advantage of FM over AM. And second case, we have a capture effect advantage of FM signal, because if we have two FM signals of the same frequency uh, is being detected by the FM receiver, then it will neglect one with low amplitude and will receive the one with high amplitude of the same frequency, two FM modulated signal, and this property is of capture effect is an advantage of FM signal. Then we have the third advantage, which is the transmitter efficiency. As we know that in AM modulated case, the AM modulated wave is being amplified by using different circuits, and that is not the case in FM, where the information is not focused on the variation of the like in the AM case on the amplitude. In FM case, it is only focused on the frequency variation. So there is no need to use amplifiers in FM case. So that is a transmitter efficiency scenario of the FM case. Then there are some disadvantages of FM case, because it has more spectrum and it conserves more spectrum and a high bandwidth than AM case, while in AM case there is low spectrum conservation as well as low bandwidth. And the second disadvantage of the FM is that the circuit used for modulation and demodulation and different kind of works like multiplexing, demultiplexing, the circuit is complex than in AM case. Now we will be focusing on our last topic, which is FM and AM applications, and we can see that there are multiple applications of AM and FM, which in which we can see that in fax machines the FM QAM are being used, which is ideal for this fax machine scenario, And then we have the aircraft radio, in which AM is utilized. In marine radio we have FM and single sideband of AM required. And then we have multiple applications in which we have different modulations which are suitable for those applications and provide ideal response in that scenario. Thank you very much.